It's amazing how far we've come scientifically in the span of only 10 years. Back in 2015, humanity didn't know whether a core prediction of Einstein's general relativity, the existence of energy-carrying gravitational waves, was true or not. We had theoretical predictions that these waves should be generated whenever a massive object moved and accelerated through a changing gravitational field, and we had observed orbital decay of binary systems, like binary pulsars, that were consistent with those predictions, but the ripples in space-time themselves, or gravitational waves, had never been directly detected. For 100 years, this great prediction of physics remained unconfirmed. Then, on September 14, 2015, all of that changed. The twin LIGO laser interferometer gravitational wave observatory detectors both saw small periodic changes in the length of their 4-kilometer-long laser arms, which heralded the arrival of gravitational waves from two black holes that had recently spiraled and merged from across the universe. With that one event, the era of gravitational wave astronomy was born, a wholly new type of astronomy that didn't use telescopes, but rather was sensitive to the ripples in space-time generated by these energetic mergers of compact objects. Now in 2025, after years of observing runs punctuated by a steady series upgrades between them, LIGO, in the midst of its fourth observing run, has just more than tripled the number of known black hole mergers, going from around 90 at the end of the third run to around 300 today. Here's how far we've come in the last decade, and how, if we don't take radical action, this era might come to a sudden unceremonious end. The story of gravitational waves begins with Einstein's general relativity. If all you have is one static, unchanging mass in your spacetime, it's going to be stable and unchanging. The mass will remain constant, and so will the spacetime surrounding it. But if you have a second mass in the vicinity of the first, they'll both accelerate due to the influence of the other, moving around through space-time, all while the space-time's curvature itself changes in response. This has a profound effect in analogy with electromagnetism. In classical electromagnetism, obeying Maxwell's equations, an electrically charged particle moving or accelerating through a changing electromagnetic field will emit electromagnetic radiation in the form of light or photons. Similarly, in classical gravity, obeying Einstein's equations, a massive particle with a gravitational charge moving or accelerating through a changing gravitational field, a region of spacetime where the curvature changes, will emit gravitational radiation in the form of gravitational waves. These waves must carry energy and must move at the speed of light. And according to the theory of general relativity, as those gravitational waves propagate away from the massive sources that generated them by their motion through spacetime, they cause the space that they propagate through to alternately expand, grow, and contract, shrink, in phase in mutually perpendicular directions. For a long time, astronomers hoped to uncover evidence for the existence of these gravitational waves. They got a whiff of hope back in 1974, when astronomers Russell Hulse and Joseph Taylor discovered a highly unusual star system, a system containing two neutron stars, where one of those neutron stars was emitting regular pulses every 59 milliseconds. Known as a binary pulsar, the arrival time of the pulses exhibited regular variations every 7 hours and 45 minutes, which led to the detection of the binary companion. Each neutron star is massive, containing more mass than the entire Sun, but extremely compact, at around approximately 20 kilometers in size. They orbit one another in a very elliptical fashion, coming as close as 746,600 kilometers, about the radius of the Sun, but reaching maximum separations of 3,153,600 kilometers, about 4 solar radii. Here's the kicker though. These orbits aren't constant over time but very slowly decay. As these large masses move through space at close separations to one another, the accelerated motion through spacetime whose curvature is changing results in the steady emission of gravitational waves, where that emitted energy comes at the expense of the orbital energy of the two bodies. Each year the orbits shrink by about 3.5 meters, and the orbital period shortens by 76.5 microseconds. Although the gravitational waves from these two neutron stars are too weak to directly detect, the observed change in the pulse periods over time provided indirect evidence that these gravitational waves must exist. However, there ought to be sources that were so energetic out there in the universe that, in principle, an appropriately designed gravitational wave detection apparatus could be sensitive to those ripples in spacetime. In particular, when a compact massive source and another compact massive source achieve very tight orbits with one another, they'll reach such small separations that either their surfaces will touch and they'll interact, or, if one or both of the objects is a black hole, one object will encounter the event horizon of the other and merge. These are the scenarios that emit gravitational waves of the maximum amount of energy, with the frequency of the emitted gravitational waves corresponding to the masses of the objects and their minimum separation distances before interaction and/or merger. In order to detect these gravitational waves, you have to understand that the waves will propagate through space, causing expansion and contraction oscillations to happen when the waves pass through. To catch them passing through, scientists concocted the brilliant design of gravitational wave detectors, sending a split laser pulse down two mutually perpendicular vacuum tubes, reflecting them back and forth many times, and then bringing them back together to construct an interference pattern. When there's no gravitational wave, the pattern remains constant, but when a gravitational wave passes through the apparatus, the path lengths change, altering the arrival time of the pulses and leading to detectable changes in the interference pattern that results. That's the basics of how gravitational wave detectors works. LIGO, with twin detectors located in Livingston, Louisiana and Hanford, Washington, used arms that were approximately 4 kilometers each in length and leveraged about 1,000 laser reflections in each one before those two laser beams were brought back together. Theorists calculated thousands of gravitational wave templates based on the types of black hole mergers, black hole neutron-star mergers, and neutron-star mergers that they expected to occur across the universe, modeling a variety of spins, masses, and orientations to them. Advanced LIGO, which grew out of the proof-of-concept prototype that was the original LIGO, turned on in early September of 2015. While still undergoing calibration, this first gravitational wave unexpectedly arrived, but the detectors were performing so well, and the arriving signal was so strong, that both detectors immediately registered the signal. Humanity had detected our first ever gravitational wave event, a merger of two black holes, one of 36 solar masses and another of 29 solar masses that resulted in the production of a 62 solar mass black hole. With just a little math, you'll notice that 3 solar masses were lost, but they weren't actually lost. They were merely converted to energy via E equals sign mc2, where that energy was in the form of gravitational waves. By transferring a tiny amount of that gravitational wave energy into the LIGO detectors, we were able to detect that signal from across the universe. Subsequently, more data was taken, and a few more events were seen. After detecting those events, both detectors were shut down and received upgrades, with some of the systems that received upgrades being the vacuum systems within the laser cavities, the temperatures and reflectivities of the mirrors, the squeezing of the quantum states that created the laser beams, and the sources of error and noise that limited the detector's sensitivity were lowered as well, making LIGO more sensitive to gravitational waves generated at greater distances. With each new factor of 2 in sensitivity that LIGO, or any gravitational wave detector achieved, it became sensitive to 8 times as much volume as previously, since our 3-dimensional space means that twice the sensitivity enables detections at double the distance in all 3 dimensions. Every new upgrade meant increased sensitivity, which meant a greater volume of the universe to probe for these gravitational wave events. More volume means more events, and that means the rate of detections only increased as these upgrades continued. LIGO was then joined by the Virgo detector, a slightly smaller gravitational wave detector in Europe, which enabled astronomers to pinpoint or triangulate, because we now had 3 detectors total, the location from which gravitational wave events emerged. By the end of the second observing run, we had reached double digits of gravitational wave detections, with the first neutron-star merger joining all of the other black hole merger we'd seen. When the second observing run came to a close, further upgrades to LIGO and Virgo were enacted, and then later on, the Cagra detector joined the gravitational wave party as well. By the end of the third observing run in 2020, a total of around 90 gravitational wave events had been seen. By this point, all 3 types of events, including neutron-star mergers, and neutron-star black hole mergers, were all seen. In a new pair of papers whose preprints were released on August 25, 2025, just 3 weeks prior to the 10-year anniversary of the arrival of the first directly detected gravitational wave, the LIGO, Virgo, and CAGRA collaborations combined to release a new catalog of their highest significance detection events of all time. Although the ongoing Observing Run 4 has detected more than 200 sources on its own, the new catalog stops with the events ending in January of 2024, bringing the total up to 218 released and vetted events, more than doubling the total of 90 from the end of Observing Run 3. The graphs you see, sometimes called eagle plots because of their shape, above and below, shows the known black holes and neutron stars below 300 solar masses. The top graph shows the ones known at the end of Observing Run 3 alone. The lower graph shows the ones as of the end of the first part of Observing Run 4. The blue points indicate black holes detected from gravitational waves. The orange points indicate neutron stars observed in gravitational waves. The red and yellow points, for comparison, show black holes and neutron stars detected through electromagnetic, light-driven signals, showcasing just how remarkable the science of gravitational wave detection has been for learning about the populations of black holes below 300 solar masses. As you can see, even from just a visual inspection, there is no mass gap where objects are completely absent. However, visual inspections are insufficient tools for determining if there's a population deficit or excess at any given mass, or across any particular mass range. If we want to determine what's present, what's anomalous, and what appears to be missing, we have to perform the appropriate quantitative analysis. Fortunately, that's what the second of the 2 released preprints, both of which are to be published in a special issue of Astrophysical Journal Letters, is all about. Indeed, there isn't a mass gap between around 5 and 10 solar masses, but there is a substantial mass deficit. There are more objects at lower masses and at 10 solar masses and above than there are masses in the in-between range. There are 2, maybe 3 spikes in the mass distribution of black holes, with a peak at 10 solar masses, and another peak at 35 solar masses, with a possible but less significant third feature at around 20 solar masses. Above 35 solar masses, the abundance of black holes drops off somewhat more steeply than the simple power law curve that describes black holes at lower masses, suggesting some suppression of those higher mass black holes. Although the ones that do exist produce the largest amplitude gravitational wave signals, making them relatively easy to spot. Some features, upon a deep analysis, stuck out. When you have a pair of binary black holes, they're not just going to orbit one another and in spiral, but each black hole can have a spin to it, and those spins, cumulatively, can be either aligned or anti-aligned with the orbital angular momentum of the binary system. When the collaboration members looked at the spins of systems with at least one black hole in the 30 to 40 solar mass range, right where the heaviest peak in the mass of black holes is found, they found that spins were only a little more likely to be aligned compared to anti-aligned, about a 65/35 split. However, for systems that didn't have a black hole in that mass range, that is, for all other binary black hole mergers, they found that spins were far more likely to be aligned compared to anti-aligned, showing an impressive 87/13 split. If you model the formation of stars that evolve into black holes, you expect that the spins of the stars, and the spins of the resultant black holes, should be preferentially aligned with their binary orbits. But if you model black holes that merge together as part of trinary, or richer systems, you expect that the post-merger spin will be much more random with respect to any remaining members. This was suggested in a paper back in 2016 and appears to be consistent with the latest data. Perhaps the peak at 35 solar masses is due to mergers of previous black holes that produced at least one member of between 30 and 40 solar masses. It's an intriguing idea, and one that's suggested but not proven by the current data. Thus far, here in 2025, LIGO and the other gravitational wave observatories around the world have continued to take data, discovering approximately 100 additional gravitational wave events, mostly black hole mergers, that aren't included in the papers that were just released. In less than 10 short years, we've gone from, we think gravitational waves exist but we've never seen one, to being able to measure hundreds of gravitational wave events, pinpoint where on the sky they occur, infer the population of stellar mass black holes in the universe, including where there are gaps and peaks in the mass distribution, and even to uncover information about the correlations between the black hole spins and the merger orbits. What was once just a pipe dream of astronomers, physicists, and general relativists has swiftly grown into a robust field of observational astronomy. At the start of 2025, astronomers had dreams of two successor facilities, LIGO 2, which would be a ground-based detector or multiple detectors with much longer baseline arms, of 10 kilometers or more, capable of seeing practically every stellar mass black hole merger within the observable universe. And LISA, the Laser Interferometer Space Antenna, which would allow the detection of more massive black hole mergers, including intermediate mass and some supermassive black hole mergers for the first time. Instead of those dreams that look forward to continued advances at the frontier of science, however, gravitational wave astronomers are instead facing the extinction of their own field, right as it's poised to take off. The catastrophic proposed FY 2026 budget contains a $9 billion cut to the National Science Foundation, with specific instructions to close down one of the two main LIGO facilities. As one astrophysicist put it, degrading LIGO's observations of gravitational waves in this fashion is tantamount to killing a newborn baby, or as another quipped, it's a senseless, irrational thing to do, like trying to fly a plane with only one wing. When you couple the proposed National Science Foundation cuts with NASA's redirection of priorities away from science and instead towards militarized projects like nuclear activity on the moon, it becomes apparent that the status of the United States as a world leader in physics and astrophysics is more precarious than ever, with even the upcoming Habitable Worlds Observatory under threat. If we abandon this new form of science now, while it's still in its infancy, progress will likely be set back by decades, if not an entire generation or more. And that's a pity, because the awe and wonder that this era of gravitational wave astronomy has brought to us is truly unprecedented. Still, despite the external pressures and threats of withheld funding, there is no diminishing the achievements of gravitational wave astronomy in the last decade. One cannot help but be simultaneously humbled and inspired by how far we've come, both scientifically and technologically, in the realm of gravitational wave detection. After all, we've learned so much in such a short time. And we've done it with a new form of astronomy that, for 100 years, was no more than an unproved prediction of our theory of gravity. The universe is full of black holes, and for the first time, we have direct, data-driven estimates of just how many there are, and of their mass distribution. All of this was only made possible by the new science of gravitational wave astronomy, which is thriving at a greater level than ever before. Even as the very field itself is at risk of a premature termination, the legacy of what we've already accomplished and the hope it gives us all for the future of science can never be erased.